Hello, welcome back again. Electrical Fundamentals, Engineering 201. We've talked a lot in the past about equivalent resistance, series and parallel combinations, current division, voltage division, Kirchhoff's current law, Kirchhoff's voltage law, and I wanted to start to put it all together with some examples. So really what we're going to do for in this lecture and the next lecture is work examples, and hopefully you're doing the same in your homework. Doing electrical fundamentals is like riding a bicycle. You can read about it, you can watch videos of someone doing it all you want, but eventually you have to grab the handlebars and pull yourself up there and risk getting scraped up and see if you can make it work. I would encourage you to work on the homework problems. Go back, and I've said it before, take a given problem like this without the work and see if you can reproduce the work. Hopefully you're reading along in the textbook in chapters 2 and 3. If you're still struggling, go back and reread chapter 1, chapter 2. Remember, we have a lab time each week where you can ask questions and whatnot. Really dig in at the beginning here. I think it will pay off well. So with that motivation, let's see if we can work this problem. We've got kind of an interesting problem here. I've got an 18 amp current source and a variety of resistors. Fairly easy problem. I mean, it looks a little cumbersome, but it's fairly easy because there's only one source. We'll find out pretty soon when we have multiple sources. Things will get more complicated. So we'd like to find here, I'd like to find the voltage VA, that's the voltage at this point here with respect to this point down here. That would be a lot like if we were to take our voltmeter and put one lead right here and one lead right there and ask for what's the voltage between that. Then VB is the voltage at this point with respect to here. So again, that would be like taking our voltmeter and putting one lead here and one lead there and measuring it. And finally, VC is the voltage at this point here with respect to that point. And again, taking the voltmeter and putting one lead here and one lead there and measuring the voltage potential or difference across there. So let's see if we can do that. Oftentimes in these problems we do this with simplification. So I'd like to turn this into a much simpler problem. We'll usually condense it down and then start to expand it again once we learn something when it's condensed down. So I'd like to hopefully get it condensed down so it looks something like this. 18 amps here, and we'll leave that 4 ohm alone, but I'd like to combine all of these resistors into one branch and all of those into one branch. So I'll have something like this. Well, if we look at the relationship of this 2 ohm resistor here and that 4 ohm resistor there, pretty obvious those are in series. This VC is just a measurement. There's not an actual path. Maybe I need to be a little more careful in my drawing. This is not touching this point here. We would just be measuring the voltage across there. There's not a path for it to flow through. Hopefully there would not be that much going through our voltmeter, and we'll actually look at a problem that deals with that in a little bit. So the 2 and the 4 are in series, so 2 and 4 in series. We add those together so we get 6 ohms right there. This one's a little more involved, but it looks like I've got the 6 and the 3 are going to be in parallel, which nets me 2 ohms, right? And then that's going to be in series with the 4 and series with the 6, so I'd have 2 plus 4 plus 6, which would give me 12 ohms. So I've got 12 ohms over there. Okay. And this is, of course, then 4 ohms. So now I know that I've got 18 amps here, and it's going to come to this point and it's going to split. Some of it's going to go down here. We could call this I1. Some of it's going to go down here. We could call this I2. Looks like a job for current division. I could say that I1 is equal to 18 amps times the other resistor, 12 ohms, divided by the sum of those, which is 6 plus 12, which is 18 ohms, gives me 12 amps. Now we know that I2, it had better be what? The difference. If this is 12 and this total is 18, this had better be 6 amps. Let's see if the math works out. Again, I would take the total current, 18 amps, multiplied by the other resistor, there's 6 ohms, and divide by the sum of the total, which is 18 ohms. And indeed, we get 6 amps. 6 and 12 is 18. So what that tells us now is the current down through this branch is the I1, or 12 amps, and then the current through here is the 6 amps. So let me again redraw this a little bit. So we'll have page number 2. And what I'm going to do is I'm going to draw something not quite as cluttered and as complicated as that, but probably not quite as simplified as that. Now that I simplified this, I've got those currents, I want to go back and I want to look at a circuit. So what I'm going to do is I'm going to draw something that separates these out so we can talk about this VC, and then has this 6 and this 4, and I think I can leave these combined. I can leave those combined at 2. So with that, I'd have something that looked like this. Okay, so this was the 4 ohms. This is 2 ohms, this is 4 ohms, 6 ohms, what do we have? 4 ohms, and then I had this 3 and 6 in parallel, which gave me 2, so I'll write that down there at 2 ohms. This was 18 amps, and I had then that this was VA. I had that from here to here was VB. And from here to here was VC. So let's see if we can get this then. I'm going to make that so it doesn't touch there if you're a little more comfortable with that. So we can say then, I'll use Kirchhoff's voltage law. And I could say if I wanted to, if I started at this point, I could go from there to there, and that would be the same as saying VA, right? VA. And that gets me up to that point. And then I know that I've got this current here. That was that I1, wasn't it? That was that same current right there, I1, so that was 12 amps. So there's 12 amps. And I know that the current through here has to be the I2. That was that I2 that we had there, or 6 amps. Okay. So what I'd like to do is I'd like to get back to this point. So if I write Kirchhoff's law, what I'm going to do is I'm going to take this path. I'm going to go up VA, and then I'm going to start to drop down. As this current goes through this resistor, it's going to be going from positive to negative, isn't it? So that's a drop. So I have minus 2 ohms times 12 amps. That's the drop there. And then I get down here and I do the same thing. I'm going to drop, and it's going to be minus 4 ohms times 12 amps. And that gets me back down to here, and there's nothing in here. This is essentially all the same point. So Kirchhoff said that's equal to 0, right? So I could say that VA, the gain across there, is essentially equal to this, what are we going to have there? 48 and 24, 72, is that right? Yeah. 72 volts. Okay. And really what we've done is kind of played this chutes and ladders game. I came up this VA, and then I dropped down there, and I dropped down there, and I know I had to get back to the same point. Okay. The next one, let's see if we can do VB. How do I get VB? Well, I'm going from here up to there, right? So let's just do that. There's VB, so I go from there to there. And then what could I do? Well, I might travel back this way. That's that 6 amps, and I'm going to go from positive to negative, so I'll subtract off 6 ohms times 6 amps. That gets me to there, and then I drop again, positive and negative, so I'll subtract off 4 ohms times, 6 amps. So I get 36 and 24 is... Well, Kirchhoff says that's equal to 0, so I'll be a little more careful here. Then VB is going to be equal to 36 and 24, which gives me 60 volts. Okay. Let's see, VC, what's that going to be? I go from here to there. Lots of different ways of doing that. I could say that VC, and then I have to look at, well, if I go from here to there, this is still 6 amps, isn't it? So I subtract off 2 ohms times 6 amps. And I go down here, and then I've turned and I've gone up. And now, if this 12 amps is going this way and I'm going up, I'm going to gain. I'm going from negative to positive, so I'm going to gain positive. And I have a positive 4 ohms times now 12 amps. Okay, Kirchhoff says that's equal to 0, so I can say that VC is equal to, what am I going to have? 12 minus 48, right? Equals minus 36 volts. So I went essentially around here. Now some people might say, well, hey, could you go a different way? We'd say, yeah. Or could we try it this way? VC, what if I went up there? I could say that I had VC and then plus VB. Now I'm sitting up there. And then I could come down through here, and I could say that that is minus 2, because I'm going from positive to negative, that's a drop, minus 2 ohms times 12 amps. That gets me back to where I started, right? So I can say that's equal to 0. So I get to say that VC is equal to minus VB plus 24. Which is, what's minus VB? Minus 60 plus 24. Does that work out? I hope so. What did we get? Minus 36 before. We got minus 36 this time. Good. Should work. Well, that's not the only way you could get VC. What if we tried this? So this is an OR. Let's try another OR. So I have VC. I go from there to there. Then I add to it VB. That gets me up to there. Well, let's try the bus down here. That'd be going from there to there. What's that? That's minus VA, isn't it? That gets me to here, which is the same point as there. And then I just have to go this way, so I'm going to go from minus to positive, so I will add to it 4 ohms times 12 amps, right? That's equal to 0, so I can say that VC is equal to minus VB plus VA minus 4 times 12 be what, 48. So we have, what do we have? VB was 60, so I have minus 60 plus VA 72 minus 48. What's that turn out to be? I hope we get the same answer. Minus 36. So lots of ways to do these, but certainly you need practice, because the polarity going from here to here being positive and going from there to there being negative is very important. Okay. The other thing it brings up is lots of ways to solve these problems. There's usually not just one way, and understanding isn't necessarily starting and then maybe peeking at the answers and working backwards and seeing if you can make it work out. Understanding is sitting down with a problem and working it one way, and then sitting down with it and working it another way and getting the same correct answer. Then maybe sitting down with a friend, and I encourage you to work in study groups, and a friend can't get the problem and you show them, hey, well, the mistake is you're not using Kirchhoff's voltage law correctly. Here, let me show you. And you get to the right answer. That's when you have real understanding. So use your pause button, go back, look at these problems over and over again, and make sure that you're comfortable with it. The other thing that I encourage you to do is to remember that these problems, it's kind of my job to make them look easy, right? So you go through this and, oh, that makes sense, that looks easy enough, and then you get to it on the test and the page is blank and you have a problem. So I'd even go back to the lecture, take this problem. We can make ourselves a little sheet here. So I just tore this paper out, lay that over the thing, and now you can rework the problem here. See if you can get to the same answer. See if you can do it correctly. So practice, practice, practice. Again, I mentioned the bike analogy at the beginning. How'd you learn to ride a bike? Well, it takes practice. You get scuffed up, and you just get back on it and keep practicing. So I encourage you to do that. Well, let's move on to the next problem. So this is a fairly simple problem from an analysis standpoint, but a good problem to talk about a conceptual issue. What we've got here is a very simple circuit. We've got a 40-volt source and a 5 k ohm. First time we're using k ohm, so 5,000 ohm resistor and a 75,000 ohm resistor, 75 k ohms. We want to make sure those units are the same, and they are. If we had 5,000 ohms and 75 k ohms, we'd want to convert one or the other into similar units. So that's the circuit itself, and then we say, well, what happens if we come along and we measure this? We put this voltmeter here. That's where we take the probes of the voltmeter, put one there and one right there. What's that really doing? Well, inside the voltmeters, there's some internal resistance, and there's this meter, which is essentially just a coil. So we'll lump its resistance into here. And if we take this resistance as 1.5 times 10 to the 5, and that is probably a pretty low resistance. We'd like it to be higher. If you look at the meters in lab, they're probably going to be a couple orders of magnitude larger than that. But anyway, for our purposes, we'll take that number. So we'd like to calculate two things. We'd like to calculate the voltage across here, VAB. What's that? That's the voltage right there. There's the voltage at A with respect to B. We'd like to calculate that. We'll call that the ideal or the calculated. So we can say that this is really equal to, I mean, this is simple voltage division, isn't it? This is going to be equal to then, what do I have? Voltage division. If I take the 75 k ohms times the 40 volts, and I divide by 75 plus 5 k ohms, or 80 k ohms. K ohms cancel, and you come up with 37.5 volts. Okay, 37.5 volts. Ideally, that's what it is. Okay, if our voltmeter did not introduce a lot of error in its very presence, that the answer should be pretty close to that. Well, let's look at the measured. The measured is going to be a little different, because all of a sudden we could just think of this as a circuit through here. I've introduced a resistance there, haven't I? So I now have a circuit that looks like this. With, let's see, 1.5 times 10 to the 5, what is that? That's ohms. So I need k ohms, so that'd be 1.5 times 10 to the 2 k ohms, which is, what, 150 k ohms. So I could say now I have 75 k here, and I have 150 k there. So when I put 75k in parallel with 150k, that turns out to be what? 50 k ohms? Product over sum, or the inverse of the sum of the inverses. So you got 50 ohms. So now I have a circuit that looks like this. I have that 40 volts with 5k. And now instead of 75k, I only have 50k. So if I look at this voltage across here, there's VAB measured, which is going to be now 50 k ohms times 40 volts divided by 50 plus 5, or 55 k ohms, which gets me 36.4 volts. Okay, so I've gone from what it should be at 37.5 to 36.4. Now this is really a good example of system loading. Okay, system loading. It's a good example to use our tools of parallel resistance and voltage division and things like that, but it's a good example of system loading. Do you have to worry about this so much when you go to the lab? You got to think about it. It needs to be in the back of your mind. It's probably not going to crop up because, like I mentioned, our meters are probably at least 100 or 1,000 times larger than this. So if you play around with that value and go to a very large resistance here, that makes this a lot better. But it's something you should have in the back of your mind and always think about. For mechanical folks in here, I mean, let's say that we have a nice steaming cup of coffee or hot cider or whatever you think about drinking, and you want to take the temperature of that. You can put a thermometer in there, right? Well, what if we took a thermometer that was a great big thermometer that was ice cold and thrust that down in there? Okay. Would that change the temperature reading? Yeah, absolutely it would. And there's precautions that we'd probably want to take there. We may want to make an estimate of the temperature and bring the thermometer up to that temperature that before we put it in. Maybe use a thermometer that has a minimum amount of thermal mass and things like that. So these are all things to think about, and in this case, a good example. Give us some practice calculations as we go through this. Well, let's look at one more problem for the day. So let's say this is page number 4. So I've got a problem here. I've got a voltage source, 72 volts. Getting into very dangerous territory with 72 volts. And remember, we talked safety-wise, only took about 1/10 of an amp. A 9 volt battery will produce what, about 500 milliamps. So you could easily electrocute someone with a 9 volt battery if for the fact that it's a 9 volt battery. If the voltage were higher on it, it has plenty of current to do that. So if we have really very much current at all here, this is quite a dangerous circuit, so something to keep in mind there. Well, anyway, this is a little bit like the problem we started out today with. I have a voltage source rather than a current source, and what I'd like to do is I'd like to find the voltage from here to here, so that would be like putting my voltage probe across there, find the voltage across there, and then the voltage across here, and finally the voltage from there to there, VA, VB, and VC. I'm going to attack this very similar to the last problem. I'm going to talk about, well, I'd like to figure out what the current through here is. Maybe I will call this I2. I'd like to find the current through here. Maybe I will call this I3. And the current through here that comes up there and goes like that, I could call that I4. So I guess you might, well, where's I1? Well, let's say that I1 is the total current here. There's I1. So to do that, I'm going to simplify this circuit. I'm going to turn it into something that looks like this, just like we did last time. Simplify it greatly. And then we'll probably have to expand it back out. I could say that I have something like this. We'll leave that 2 ohm resistor there. These two are definitely in series, right? So I have 4 ohms there. So there's 4 ohms. There's the 2 ohms. And we said that was, what, I2? And this is I1. Then what about this branch here? Well, let's see. These two are in parallel, so what's 6 in parallel with 12? That gives me 4, doesn't it? Product over sum. 4 in series with 1 is 5, and in series with another one is 6. So I now have 6 ohms, and that's going to be, what do we call that, I3, right? And then finally, let's see, current that goes up here, it goes through an 8 ohm and a 4 ohm, so that's going to be 12 ohms, isn't it? So I would have 12 ohms. We said that was I4. Okay. Well, let's see, I may have to do some more work. Why don't I simplify this yet again? Do 72 volts. I have a resistor here and a resistor like that. This is 2 ohms. And what do I have? I have 4 and 6 and 12. Let's see, 6 in parallel with 12 is going to give me 4. Product over sum, 4 and 4, that would give me 2, wouldn't it? So I could say that this was 2 ohms. Or you could get that as 1 over 4 plus 1 over 6 plus 1 over 12, right? No matter how you do that, you should come up with 4. Not 4, I'm sorry, with 2. Yeah. Okay, so now if I have 2 ohms there and 2 ohms there, I can figure out the voltage across there. That's going to be 72 times 2, resistance there, divided by the total resistance is 4, which turns out to be half of 72, which is what, 36? Anytime you have 2 resistors, the voltage split is going to be even. It'll just be half. You'd have 36 across there and 36 across there. Well, the reason for doing that is now I know the voltage across here. If I want to get the voltage across there, that's 36 volts. The voltage across there, that's 36 volts. So I can say then that I2 is equal to 36 volts divided by what? 4 ohms? Which is going to be what? 9 amps? That I3 is equal to, should be 36, there we go, 36 volts divided by 6 ohms, which gives me 6 amps, and that I4 is equal to 36 volts divided by 12 ohms, gives 3 amps. So I could say then that the sum total of these, 9 and 6 and 3, is 18 amps, isn't it? So I1 is equal to 9 plus 6 plus 3, which is 18 amps. Does that make sense from this picture? Well, if I talked about this current there, there's I1, isn't it? I could say that I1 would be equal to 72 volts divided by the equivalent resistance, which is 4, right? 72 divided by 4 would be 36 divided by 2, 18, yeah. 18 amps. Good. So now we're not done, but we've got an important piece. I know that what I1 is, I know what I2 is, and I know what I3 is. Let's see if we can finish the problem then. Let me put the information back over here that we have. So, and I really, in this picture, I just assumed I1 and I2 and I3. I tried to avoid negative signs. If you end up with a current going that way, you'll get a negative sign. After some experience, you start to figure out ways to put those in so you don't get the negative signs. But I just rather arbitrarily put those in. So let me go back and put what we found. We found that this current here was what? 18, right? Didn't we say that was I1? I1 was 18. And then the current here, I2, what did we get with that? 9. And then I3, that was 6. And finally, I4 was 3. Does that make sense in terms of Kirchhoff's law? 18 comes in, 9 of it goes here, 6 of it goes there, and 3 of it goes there. I mean, this is just like a entryway or vestibule. If 18 students come into this point, 9 of them go down this hallway, 6 of them go down that hallway, what would have to go down this hallway? Well, it'd have to be the remaining 3, wouldn't it? Okay, so that holds up with Kirchhoff's law, and we can start to solve the problem. Very similar to that first problem. Now that we have the currents, we could talk about VA. So we got lowercase there. There's VA. I don't want the equal sign because I'm going to put it in an equation. So we've got VA, so I go from there up to there, and then I need to subtract off what? 2 ohms times 18 amps. Is that right? Because the current's going to go from there. It'll be positive and negative, so it will subtract off. And then I'll turn and go this way. So I'll subtract off again 1 ohm times what? 9 amps? Gets me to my starting point. So Kirchhoff says that's equal to 0, and I say then that VA is equal to what? 36 comes positive going on to the other side, plus 9, which is what? 45 volts. Is that right? 36, 46, yep, 45 volts. Good. What about VB? We can do VB just as easily. And granted, there's other, you could say, well, what if I went around here? And there's all kinds of different paths, and this would be a good problem to practice those different paths. Well, let's talk about VB. So VB, I go from there to there. And then what do? I could say that I have positive because this current's going to cause me going from positive to negative. So now as I go this way, as I go to the left across that, I'm going to have positive 1 ohm times 6 amps. And now as I turn and go down this one, I'm going to go from positive to negative, so that's a drop, minus 1 ohm times what? 9 amps. Okay, so this 18 amps goes with that one, 9 amps goes with that one. Kirchhoff says that's equal to 0, so VB would be equal to a minus 6 plus 9, which gives me 3 volts. Okay. Now, this is one where you could have easily, if you wanted to, instead of going back around here, you could have turned and gone around there if you wanted to. Although I'd have to do, well, I guess we know that this is really, what, a 4 ohm resistor in there, so we could get through that if we wanted to. Well, let's finish up with VC. VC, so I go from there up to there. What can I do with that? Well, I guess I could recognize that this is what? That's 6 in parallel with 12 product over sum. That's 4 ohms, isn't it? So I could say that I have, going from there to there, and I've got this current here, so it's going to go positive and negative, so I'm going to have to subtract off 4 ohms times 3 amps. That gets me down to here, and then I've got to go back up through this equivalent resistance, which is going to, that's going to go from what? The current's going this way, so it's going to go from positive to negative. So I have to gain 4 ohms, that's this one, times 6 amps. Kirchhoff says that's equal to 0. So VC turns out to be equal to 12 minus 24, which gets me minus 12 volts. Minus 12, we don't have a lot of negative answers. If you were to again use the voltmeter analogy, you put the voltmeter there, you'd probably see negative on the screen. If we switch the leads, you'd see positive, which really meant that we were just put the arrowhead on the opposite end. Well, let's see. Could I do this differently if I wanted to? Could I go from there to there, and then maybe from there to there, and there to there, and over to here, and then over to there? Absolutely. Lots of different ways to do this problem. And maybe I'll leave it at that, let you look at some of those ways. These answers are sound here. VC, double check. Let me double check these. Minus 12, 3, and 45. Yeah, so play around with this. See if you can take a different path. Instead of coming around VC, instead of coming then around here, back over to there, see if you can go the other way. See if you can come around there. That would be a good exercise. And in the end, you should get the same answer. Well, those are hopefully some good sound problems, give you some practice with examples, carry that on into some of your homework problems. When we get together next time, what we're going to talk about is a little more complicated problems, and problems that will really usher in more advanced analysis techniques, the techniques of node analysis and mesh analysis. So take care till then, and thank you for watching.